Hi everyone, my name is Jai Zhang. I'm here today with Rohini Das to present our study that investigates knowledge reasoning models' predictive performance when a student starts a skill. As many of you have already known, knowledge reasoning is a critical component in adaptive learning. It utilizes students' previous performance to estimate their proficiency on latent knowledge and infer their likelihood of success in future attempts within a learning system. Three categories of knowledge reasoning algorithm have emerged over the last decade: BKT, PFA, and a set of modern algorithms that are built based on neural networks such as DKT and DKVMN, which has shown to have a better model fitting compared to more traditional algorithms. However, we think the current way of using the overall success to compare algorithms may be a problematic practice. For one, studies don't normally report the sample size for all skills. Even in large data sets, there are skills that students only encounter once or twice, and accurately predicting the first or second time a student encounters a skill reflects something different than accurate prediction after the student has had more practice. And we refer to this situation as a co-star problem, where models need to perform well before having sufficient data for the current student. And it is possible that more recent algorithms may perform better in this situation, either by using information from students' performance on other skills or information on properties of specific items. Therefore, in this study, we explore the co-star problem in knowledge reasoning models. Specifically, we study how the performance of three knowledge reasoning algorithm changes depending on how much data the algorithm have on a student's performance on the current skill. In our analysis, performance matrix AUC and RMC are reported for each attempt on a skill. We examine if performance changes as the number of attempts increases, and more importantly, by comparing across models, we examine if the better performance in modern algorithm is due to their better fitting at the initial stage. Now let's move to the methods.
In this research, we used the Assessment Skill Builder 2009 to 2010 dataset, and we sorted the data by the number of times a student encountered a problem that practiced a certain skill, which is known as the instance. To see how the performance of KT models changes depending on the amount of data the models have, we built each of the three models with five-fold student-level cross-validation. Finally, we averaged the AUC and RMSE values across the four skills in each instance. This graph displays the number of students per instance in each skill for the assessments dataset. Looking at the graph, we can see a drop in sample size as the number of instances increases. In fact, between the third and eighth instance, we observed an average attrition rate of 20 to 45% across the four skills. This graph shows the average AUC values at the first 8 instances for the BKT, PFA, DKVMN models. Here, we can see an upward trend in the AUC. Starting at the first instance, the AUC value of the DKVMN model is significantly greater than that of the other two models, by approximately 0.15. Thus, DKVMN is better than BKT and PFA and making an initial prediction the first time a student encounters a skill. In the following instances, we see the values of BKT and PFA grow closer to DKVMN. In fact, by the fourth instance, all three models' AUC values were fairly similar and had a range of 0.65 to 0.7. While DKVMN started off higher than BKT and PFA, the AUC values of all three models grew closer to each other with each instance. Here are the average RMSE values at the first 8 instances for the three models. Looking at the graph, we can see a general downward trend in RMSE with each instance. While the RMSE of DKVMN starts off lower than that of BKT and PFA in the first instance, but fourth instance, the RMSE of all three models is in the range of 0.43 to 0.46. Thus, similar to AUC, the RMSE results display that while DKVMN is better at making initial predictions than the other two models, the values of all three models grow closer with each instance.
So, to reiterate, let's use the AUC results as an example. We see in all three models, predicted performance increases as the number of attempts increases. But more importantly, compared to earlier algorithms such as BKT and PFA, the modern algorithm DKVMN has a strong advantage on making prediction at the initial stage. However, the difference in performance becomes smaller after the first two attempts, and the performance are essentially the same by the eighth attempt. So, what does that mean, and what are the implications? We believe the better performance at initial stage is a possible factor that contributes to the higher overall performance for modern algorithms. And also because of their ability at utilizing information across skills, which gives the better performance at initial stage, they are better at deciding what skill to work on next and for building detectors such as gaming the system where accurate estimation of students' current knowledge is needed. But when algorithms are used for the purpose of estimating mastery learning, modern algorithms might be just as accurate as traditional algorithms. Lastly, in future model comparisons, in addition to reporting the overall performance, we suggest a separate analysis that excludes prediction on the first two attempts from the overall performance to reflect a model's quality for use in mastery learning. Thanks for listening. Please email us if you have any additional questions about the study.